The last rock type is metamorphic rocks. These are rocks that record the story of mountain building and plate tectonics. Okay, so at depth, temperature and pressures are high enough to metamorphose rocks without melting them. So there's a recrystallization where minerals can change, textures can change within the rock and not melt them. If the rock gets melted, it's a different rock type. That's called a migmatite, partial melting, and then if it melts all the way, we go to igneous rocks. These rocks then that are experiencing metamorphism are just trying to adjust to a new equilibrium. They're out of their comfort zone and they're going to get changed by heat and pressure and maybe some circulating fluids. So most metamorphic rocks, looking at the text below, are going to form at convergent plate boundaries where there is subduction of oceanic crust or where two continents collide. That's going to make metamorphic rocks. Convergent plate boundaries are going to push rocks deep into the earth. They're going to squeeze rocks, and so they get heated and they get pressure. Metamorphic rocks are also some of our most beautiful rocks. This rock here has beautiful kyanites and garnets in it, and it's just a stunning specimen of a metamorphic rock. Really unique mineralogies and metamorphic rocks. So causes of metamorphism. I'm going to turn my face off so we can see the whole slide. Sediments and sedimentary rocks are in their happy place at the Earth's surface, right? Igneous rocks are going to be at equilibrium at the temperatures in which they crystallize. So if you take sedimentary rocks away from the surface and squeeze them and add heat, there's going to be a change. If you take igneous rocks and you squeeze them and you heat them, there's going to be a change. So the diagram below shows those different metamorphic conditions. And notice there's some labels on here. In the background, these words hornfels, amphibolite, granulite, those are areas on this temperature pressure diagram where a certain assemblage or suite of rocks are known to form during metamorphism. So temperature increases to the right and depth and pressure increases top to bottom. On here also are these dotted lines showing high temperature, low pressure, like a Hornfels, and then the middle here is high temperature, high pressure, and then to the left is low temperature, temperatures being low, and then increasing into high pressure. Most of this metamorphism is going to occur in the top 10 to 30 kilometers of depth from the surface of the Earth. Okay. All right, temperature. So temperature increases the deeper you go into the Earth. It's going to increase at different rates depending on the setting. So in the middle of continental crust, typically we're going to have a lower geothermal gradient than you would at, say, a plate boundary like a subduction zone where the rate would be higher. The average rate is about 30 degrees centimeter per kilometer, and metamorphism then begins at about 6 miles or 200 degrees Celsius. During metamorphisms, the atoms and the ions are going to recrystallize to get to that new equilibrium at that new pressure and temperature. During that, some different things are going to occur. Maybe new minerals are going to grow, or maybe new textures are going to grow. An example that happens pretty common in metamorphic rocks is that clays are going to turn into mica minerals like muscovite or biotite. A geologist can look at the minerals that form at these different pressures and temperatures and use them as geothermometers. So a geology thermometer that tells the geologist the temperature of crystallization. They also can be geobarometers that tell us the temperature, the pressure of crystallization. I'm going to go through some examples of different kinds of metamorphism Regional metamorphism, this first one here is we're looking at in the image the tip of Nova Scotia, which is still within the Appalachian Mountains. And typical of convergent plate boundaries, like where the Appalachian Mountains form, you're going to see, I'll put my face back on. Okay. You're going to see different zones that are going to record temperatures and pressures across an area of mountains, across a mountain chain. Okay, so on here are some terms. These metamorphic zones are designated by the minerals that are found there. So the examples here are chlorite, biotite, garnet, andalusite, sillimanite. So each of those is a geothermometer, a geobarometer, a mineral that we know the pressures and temperatures that it formed. And if you have an area of rocks, you can map in the rocks, and that is the metamorphic zone. Okay. So the text of the slide here, it's the most widespread happening at these convergent plate boundaries. So all the Appalachian Mountains, there's certainly some igneous rocks, but mostly they're metamorphic rocks. So metamorphic rocks are the rocks of mountain chains. At convergent plate boundaries, then, we have these linear zones of regional metamorphism, like the linear zone that is the Appalachian Mountains from basically below the coastal plain and into Texas, and all the way up to Newfoundland beyond Nova Scotia. Another example of metamorphism is contact metamorphism. In contact metamorphism, you would have like this reddish colored dike, like we saw when we talked about igneous intrusive rocks. So here's a dike. It's intruding into this light off-white country rock, and it's cooking the edges. The heat is transferred from that intrusion into the crunchy rock. We get kind of a bake zone. That gray area is a bake zone on the outside of that intrusion. Okay, metamorphic rocks are classified by their textures, and these are going to grow during metamorphism. The rock is either going to be foliated or not foliated, and that gives us the beginning of classification of metamorphic rocks. Foliation is an alignment of platy minerals, and those platy minerals are usually going to be the micas like muscovite or biotite or chlorite. And when we squeeze an igneous rock, imagine these are all the little platy minerals here, plates of minerals. When we squeeze it, they're all going to line up in like a stack, like these post-it notes, right? So we could take like a deck of cards and line them all up, flatten them out. That would be the metamorphism. So the pressure occurs perpendicular to that foliation plane. We call that alignment foliation. So here is a rock. There's the foliation, and here is the angle of the pressure during, say, continent